Welcome to the 2017 AP Statistics FRQ exam. In this video, we're going to tackle question number 5, fully explain the answers. Really good question. I'm not going to lie, kind of a harder one, but that's because it's a chi-square test. And a lot of students learn chi-square test at the very end of the year, and it kind of gets rushed a little bit, and there's some confusing parts of it. So I'm going to do my best to explain this. If you are looking for a much more detailed explanation over what chi-square is all about, please pay attention to some of the videos that are going to be popping up here in the corner for you to watch as well. Because in this video, we're just going to tackle the problem and look at the solution going through a chi-square test. All right, so here is the question. The table and the bar chart below summarize the age at diagnosis in years for a random sample of 207 men and women currently being treated for schizophrenia. So again, what we did was we looked at 207 people who have schizophrenia. We looked at their gender, females versus males, 119 women, 88 males. Then we looked at the age in which they were diagnosed, the age that they were first diagnosed. So we saw 99 total people diagnosed in their 20s, 63 in their 30s, 30 in their 40s, and 15 in their 50s. We also have a segmented bar graph that shows the proportions as well, breaking it down by each age category, again, age at diagnosis, and the percent of people at that age that are men versus women. All right, now here comes the question. Do the data provide convincing statistical evidence of an association between age group and gender in the diagnosis of schizophrenia? Now, let's first make sure we understand that this question is all about independence between two variables. Now, independence means that there is no association. If two variables are not related at all, they're said to be independent and they have no association. So our question is saying, is there an association, which would mean, do we not have independence? Now, it does want us to provide convincing statistical evidence, but we can actually kind of answer this question based solely on looking at the data. So if we look at the data, we actually should pretty easily see that there is an association in our data. We clearly see that in the older age groups, you're more likely to be a woman. So if you are first diagnosed with schizophrenia in your 40s or 50s, you have a much higher proportion of those people that are female versus male. And in the 20 to 29 group, it seems to be about 50-50. And the 30 to 39, again, the older you get, it seems that you're more likely to be diagnosed as for a female. So we do kind of see that association in our numbers, but again, remember the whole point of inference is just because you see something in a sample doesn't necessarily mean it's true for the larger population. That's, of course, why we have to conduct a test to actually determine this. So this is what we got. We got a bunch of data in front of us, and we need to determine if there is an association, yes or no. All right, first off, why is this going to be a chi-square test? Because we're looking at counts. These are counts of data. 46 women were counted, 20 to 29 women who were diagnosed in schizophrenia at that age group. All of these numbers are counts, right? And we also have more than one. We don't just have, hey, proportion of men versus proportion of women, right? Okay, then we could do a 2-sample z-test for a difference, but we're looking at way more than that. In fact, we actually have 8 different categories for the 2 genders and the 4 age groups, creates 8 categories, 8 different cells that we could see here. So to conduct a test with multiple counts, a chi-square test is the way to go. All right, so let's briefly remind you what this is going to be. This is going to be a chi-square test for independence. There are a couple different chi-square tests. We have one for homogeneity, and we also have one for goodness of fit. This is an independence test because we're clearly looking at an association versus not, which is independence. Now, there are 4 steps to a chi-square test. Very familiar 4 steps through any type of testing format. But step 1, name the test and give the hypotheses. Step 2, check the conditions for the test. Step 3, actually find the chi-square value and the resulting p-value, because you always need a p-value to make your conclusion, which is, of course, step 4. So we're going to walk through those 4 steps for this set of data. All right, so step 1, recognizing that this is a chi-square test for independence between age group and gender in the diagnosis of schizophrenia. So I'm first off recognizing that it's a chi-square test for independence. Again, why independence? Because it's asking about there being an association or not, and that is what independence is all about. So your null hypothesis in this situation is always that, yes, you have independence, which means no association. So I wrote there is no association, which is independence, between age group at diagnosis of schizophrenia and gender for the population of people being treated for schizophrenia. Now, notice that I ended at the end there with for the population, because tests are always about what is true for your population. You're using a sample to try to make a judgment about the wider population. So my null is that there's no association between age group of diagnosis of schizophrenia and gender for my population. And the alternative is that there is an association, which could also be said as not being independent, between age group at diagnosis of schizophrenia and gender. So keep in mind, no association is the null. You always say, no, everything's fine. These two variables aren't affecting each other. And the alternative is, no, these two variables are affecting each other. But make sure you also have that context in there as well. Now, as opposed to tests for means and tests for proportions, there are no symbols here. We write the hypotheses in sentence format, including all that rich context, and really making sure that those hypotheses are referencing the population of people. Because it's pretty obvious in our data, like I already said earlier, that our sample shows that there is an association. But we're trying to figure out if that association in our data can infer that to the greater population. That's why we have to conduct a test. All right, step 2 is the conditions. First condition is pretty simple. The sample is randomly selected to avoid bias. Okay, great. Second condition is that the expected counts for the 8 cells in the table are all at least 5. So that's a big condition with chi-squared tests, is that all of your expected values have to be 5 or more. So I actually have to do that. I mean, it's fine that I said it, but I actually have to prove that to you. So this is where we start with the blank table, right? So notice that all my margins are fine. Those are my totals, total of each age group, total of each gender. But now I got to figure out if my null is true. If the null is true, because that's always what you assume in any hypothesis test, what would these numbers shake out to be? Again, go back to the original data. These numbers indicate in my data that there is an association. We need to assume there's no association. So it's actually pretty simple. Hopefully you were taught well. But to figure out, for example, this first cell right here, I'm going to take the row total times the column total divided by the grand total. So again, just grab your calculator. You're going to take the row total, which was 119. I almost forgot it there. 119 times the column total, 99, divided by the grand total of 207. So just remember that formula. Pretty simple. Row total times column total divided by grand total. So that gets me, whoa, I did that wrong. I did 999. I'm so sorry. 119 times 99 divided by 207. And I get 56.91. We always have to go 2 decimals there for accuracy. So 56.91 people were expected to be in that cell if there was no association. And I'm not going to bore you by going through it all because it does take a little bit of time, but you got to do row total times column total divided by grand total for every single cell. So for the men 2029 would be 42.09. Women 30 to 39, 36.22. So this does involve, again, some math, but that's part of the process. That's part of why chi-squared is a little bit more tricky, a little bit more difficult, definitely more time consuming. So again, how am I getting all these numbers? Well, I got them written down, to be quite honest. But again, what I did to actually get them was for each cell. So for example, I'm trying to find this cell right here, 119 column total times 15 row total, or 15 is the column total, 119 is the row total. Multiply them together, divide by the grand total. So here I get 8.62, and then here I get 6.38. Now, I have to check those numbers because I need all of those expected values to be 5 or more, but it's also worthwhile to do because to get your chi-squared in the next step, I have to literally do all of that math right there. Anyway, I'm going to need all those numbers. But the condition does need to be checked. That's why I like to do this step now, that all of my expectations to assume that there is no association would be 5 or larger. All right, now moving on to step 3, actually calculating chi-squared and getting your p-value. So chi-squared is all about looking at your observed values and your expected values, and you're trying to determine how different are they. So for example, if we look at women 2029, we observed 46, we expected 56.91. That's kind of a 10 person difference. And that's the whole point is, we allow for a little bit of wiggle room. Just because you see something in a sample doesn't guarantee it's going to be true for the population. There's always going to be a little bit of variation. That's the whole point of, samples vary. But it's when there's too much overall variation, then we might come down and say, well, wait a minute. These observed numbers are just too different compared to the expectation numbers. Therefore, we're going to reject the null and go with the alternative. And that's what chi-squared is all about calculating. So remember, there's a chi-squared formula, pretty simple form that is on your cheat sheet for the AP Stats exam. And it's the observed value minus the expected value squared, all divided by the expected value. Then we have to do that math for every single one of these cells. Observed minus expected squared divided by expected. Then we have to add together all of those values to get our grand total chi-square. So I'm going to teach you a couple different ways to do this. So one, here's me literally doing all the math by hand. Kind of annoying, definitely time consuming, but I'm going to be super accurate. So I started off with that first cell. 46 was the observed, minus 56.91 was the expected, squared, divided by 56.91. Now, let's go and actually do that on the calculator real quick here. Make sure you use parentheses because you do have to square it. So 46 minus 56.91. Close that parentheses squared. And then after the square, you can divide by the 56.91. And again, you get 2.09. I'm going to go with I had 3 decimals, 2.092. All right. I got to do that 7 more times because I got 8 total cells. I got to do that for every cell. So here's all of my work for that. Again, every cell observed minus expected squared divided by expected. It does take considerable time to do this. I know it's not fun. I know it takes time, but it is what it is. Then you have to get all of those individual chi-squareds. I rounded them all to 3 decimals. And then you add them all together to get your chi-squared. Okay, 10.882 is my chi-squared value. A lot of math going on there. Lots and lots of math. I am going to teach you a pretty simple cheat for this. There's a couple different cheats on your calculator, but I'm going to teach you one that gets it for you pretty quickly. There are some others. And again, that could be saved for a different video, obviously. But here I go. First, enter stat, edit. Enter in your observes, enter in your expected. So in list 1, I literally entered in my expected values. And then next to them, I put the list 1 was my observed values. List 2 is the expected values. They don't have to be in any specific order at all, but next to the observed has to be the proper expected. So that's the only thing that matters. So again, next to the 46 females, 2029, next that was the 56.91 that we expected. So that does have to be consistent. So you still have to calculate all of those expected values. So once you have them in list 1 and list 2, here's how you can get your chi-squared pretty quickly. Your calculator could do a whole bunch of math for you at once. So first, I'm actually going to have the calculator create a summation. So second, stat, slide over to operations, and then slide over to math. This is where we're going to get our sum command. So we're going to sum up. Now, here's how we're going to get all the values at once. We're going to actually have the calculator do list 1. Those are my observations. Minus list 2. Those are my expectations. Close that parentheses squared, divided by list 2, again, was my expectations. So again, I'm literally having the calculator take all of list 1, all of my observations, subtract all of list 2, the expectations, square all of that data, and then divide by the expected value back in list 2. But I put that little sum in front because not only is it going to do all of that math for me, it's then going to sum them all together for me. So that's a nice quick way that you can get that 10.882 without doing all the individual math work. The only thing I had to do was get the expectations. List 1 is observed, list 2 is those expectations, and that working with your lists gets that done pretty quickly. All right, now I got to find my p-value. So when you're working with a chi-squared, we're going to go ahead and get chi-squared CDF. It's number 8 on, again, second vars. Second vars. Scroll down to number 8, chi-squared CDF. Remember chi-squared curves, hopefully you're properly taught this, they're all skewed to the right. So we could only ever look to the right. Again, it's chi-squared. Squares are always positive, so we can never be negative. So we're always going to go to the right. So we're going to start at our chi-squared value of 10.882. And we want to basically go to infinity. I'm going to use a 999. I want to go way to the right. Listen, if you can use a 99, it probably shouldn't matter. But I'm using 9, 9, and 9 to just to emphasize I'm going way to the right because chi-skewed models are skewed to the right. So I want to go way, 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 way to the right. And the only other thing you need is the degrees of freedom. So let's talk about degrees of freedom real quick. So how do you find degrees of freedom? You do each category minus 1 times the other category minus 1. Multiply those together, we get 3 degrees of freedom. So let me go back and explain that real quick with my table. Let's go right here. So across the top, I have 4 different age groups. I'm going to subtract 1. 2 different genders, subtract 1. So it's categories across the top minus 1, categories across the left minus 1, multiply those together. So 4 minus 1 is 3, 2 minus 1 is 1, 3 times 1 is 3, therefore I have 3 degrees of freedom. So a little bit weird degrees of freedom formula there, but that is the formula to use. So when I go back over to my chi-squared CDF, I'm going to type in 3 degrees of freedom. I'm going to go ahead and hit paste, and I'm going to get my p-value, 0.01238. All right, that's how you get the p-value. That's how you calculate chi-squared. A lot of math going on there, I know that, but hopefully it's not too bad, and hopefully you could use that cheat on the calculator to make it a little bit faster if you know what you're doing. Now, I have to make a conclusion, and this is where we get into a little bit of an issue, because if you go back to the original problem, they actually never gave me a significance level, which is kind of shocking. Usually on the AP test, they do give you a 1% significance level or 5%. This means you kind of get to pick. So you actually could have 2 different solutions here for this particular problem. Here's what I wrote. I like to go, if I'm not given a significance level, just personal preference, I go with 5%. So I said, since my p-value of 0.01238 is less than 0.05, I will reject the null. This to me is significant. There is strong significant evidence from this sample that there is an association between age group at diagnosis of schizophrenia and gender for the population of people being treated for schizophrenia. All right, so this is, again, a little weird because I went with 5%, and at 5%, I'm going to reject the null. And when you reject the null, that means there is evidence for the alternative. My alternative was that there is an association between age group at diagnosis of schizophrenia and gender. Now, again, remember, when you conclude a test, you're saying that it's true for your entire population. So this is true for the population of people that are being treated with schizophrenia. That's my population, people being treated with schizophrenia. Now, if you did go with a 1%, which you could because it was not specified, you would therefore actually say that my p-value of 0.01238 is greater than 0.01, and you would fail to reject the null. You would say that there is not enough significant evidence of an association between age group at diagnosis and schizophrenia for gender. So 2 different possible conclusions that you could have here. Both would be acceptable depending on what you went with alpha. My rule of thumb, though, is if you're not told a significance level, go with 5%. But there is nothing stopping you from using 1% level of significance if you want. And in this situation, that would cause us to fail to reject the null. Just make sure that you're wording your conclusion in context. That's the most important thing to any of these tests, is that you're not just making blanket generic statements, and you're making statements that are in context and for the population that the data came from, people treated with schizophrenia in this specific problem. All right, that's it for this problem over chi-squared. Again, please pay attention to more videos that I have made that really do a deep dive into why and all the different ins and outs of chi-squared tests, especially if you're interested. But this is a tougher problem, but if you know how to run a chi-squared test, this actually is a pretty easy problem. All right, talk to you later. See you in the next video.